in my eye. Yeah, when we were playing, a ball came and hit my eye.
Oh, really?
So yeah, so so I had retinal detachment right immediately.
Tennis ball?
It's a rubber ball, like probably.
This bounce back.
Yeah, that bounces back, smaller than tennis ball. If it was a tennis ball, it would have been nice because our eye socket will see it.
Yeah.
So this was small enough and came and right, hit my eye. So I not blame. I don't blame myself for it. So it's 15 minutes. No, 10 minutes. Do you know what this diagram is on the board?
Looks like solving triangles, finding the area of triangles within a triangle.
Yeah, there's a triangle inside a triangle inside a triangle, so that's called a Sierpinski triangle. Right, that triangle, and then you remove one piece out of it. Again, you remove one piece and keep doing this until infinite. What will be the area of such a triangle?
Well, a triangle is 1/2 base times the height.
It's a nice problem to explore, or it's straightforward. Most of you can with the existing knowledge, or with the knowledge of high school, probably, if not high school, first year undergraduation. You should be able to do that.
Looks like you just iterate that.
But the answer is kind of nice. Maybe I should say non-trivial. It will tell you why it is called a fractal. Fractal, why is it called a fractal? That's something that you can kind of inquire.
Everything looks the opposite way we planned.
Yeah. That shortened my lecture. I think I'm preoccupied. I'm thinking what to delete.
No, it's connected with the charge. Oh.
It's connected with the charge.
Remote. Yeah, that was.
Batteries.
I need to put the computer for. Oops.
Yeah, it helps.
Oh, you can increase, so I think they want
You
it
can do the
max.
full screen double click.
Can you see that?
You can say, okay.
Oh.
No, it's okay.
Just
You can
close
say,
it.
okay.
Yeah, she can see that. She can see the cross, so.
Yeah. We feel like you are in the first row of the cinema hall.
What do you call it? First row of it.
In the cinema, you have the big screen. And the first time, if you are in the first row, if the car is coming, if you.
You can feel the.
Watching 3D movie.
Yeah.
That's it.
Okay.
What's remaining? 11. Yeah.
Almost 11 and 12.
10, yeah, almost 11 and so.
10.
Homework 12. Oh, I had posted this, right? That's what you want. This is officially you on this stage, non-officially you can take it. Time, finish. No?
No. Sorry.
And, yeah. Exam is take home course.
Do we like taking late submissions?
This one?
Take home.
Before the.
Okay, from this point on, you can submit anytime you want. But let's say before the final exam. If you submit it before, it is easier
Yeah.
for me, then I can grade it.
Yeah.
So otherwise I'll wait until then. So finish it off, it doesn't help much. Everything that's due from this point on, it's available on the solution is available somewhere on the other, either mostly in my lectures. Like including today, so this homework. This homework, there is a resource, so the very first line of the homework, there is a video link. It basically does most of the steps for you. There I do quadratic and you have to do cubic, but then probably I will do cubic today here. So it's like cubic. And whatever is the next homework, that's on special relativity, again, that's mostly from lectures, so you should be able to look into the past lectures and. Okay. But nevertheless, try to follow it, what is going on, not too much detail, like because the time's limited, you cannot think too much on it, but simple things, because I can ask some example, there is 2 questions I have asked, like one question can be, look for simple questions that I expect or that you're expect, no, just because you attended the lecture, that's the way. Okay. So, we did Kepler problem, and mostly what we said is this is Kepler problems. That's not what we want to do today. We want to modify this bit, but let me quickly remind ourselves what we meant by Kepler problem. We said there's a two-body problem. So, problem. It involves M1 and M2, and there is an interaction energy, and that is given by is a specific interaction energy that's equal to minus alpha over R, where alpha is equal to G M1 M2 for gravity. If it was electrostatic interaction, then it is K Q1 times Q2, where K is 1 over 4 pi epsilon. This should be, you should make sure that you don't confuse this with the effective potential that I talked about. This is the actual interaction potential energy. Now, this is Newton's law of gravitation. That's the most important things, and the motion of planets can be understood in great detail with this. But there are still open problems even today. One of the most important open problem is that our universe is expanding. What does that mean?
Extra planet and community are.
No, if you look at all the things around us, everything seems to be moving away from us. Everything.
It's all redshift.
It's all, you use redshifts to measure it, that's
Yeah.
correct. For our purposes, let's make it simple, everything is moving away from us. And the only explanation we have for that is that our universe must have started from a smaller size and there was a, let's say, an explosion and everything is moving away from us. That's good enough. That's called the Big Bang. So Big Bang is considered as one of the classic explanation for whatever we see around us, that everything, every star that you can measure or see is going away from us. So that was okay. That is actually nice. I
You
think
can
that
actually
explains.
observe the Big Bang. Called the cosmic microwave background.
That's correct.
Yours.
Like okay, now what is cosmic microwave background? So if there is such a Big Bang, so somewhere very early, it must have been really small, our universe. So if there is an explosion, you can think of it as it must have been really small sometime very early. As you make things smaller and smaller, think of thermodynamics, it gets hotter and hotter. So you should be able to see very high energy, let's say particles or light coming from the very past. And why, what do I mean by past? As I see, the explosion is getting earlier and earlier. So there is an explosion, it happens in time. So that means whenever that explosion happened, that's the beginning of our universe. Today is when we measure those things. So an explosion happens, we are inside of that, remember? And a light starts from one point and travels to us, which we are inside that explosion. The amount of light takes is the age of the universe in a sense. And we can measure these things and these are all consistent and it turns out to be 10 raised to 17 seconds. Okay, that's that number you can think of, or usually you say it is 13 billion years. So 1 year is about 10 raised to 7 seconds. So it is 13 billion years. But going back to what Ryan was pointing out, it's kind of nice. So as you go further back in time, so there was an explosion and we are 13 billion years down here. But you can think of the explosion getting smaller and smaller, energy getting higher and higher. So there must be photons which were very high in energy at that time. And they were so high in energy that they, even if hydrogen atom existed, it will come and hit the hydrogen atom and make it into ions, protons and electrons. So hydrogen atom is not stable enough at that high temperature when it was really compressed. So there must have been a very sharp time, a very critical moment when the energy of the photons became less than the ground state of hydrogen atom, and then it cannot break it anymore. And that is what we see as cosmic microwave background. So if you see around us, there is this whole radiation around it, which cannot interact with anything because the ground state of energy is higher than all those energies. So there's a critical energy, and that's called the cosmic microwave background.
I think they measure is, isn't it also the temperature of space too? around
Yes,
you,
that
which
can
is
be
about
used to,
2
that's
Kelvin?
an energy, so you can relate it to temperature. So you can say that's the temperature of the space. It comes out to be around 2.7 degree Kelvin. And it has a lot of properties. You can do various measurements. It is all consistent. The Big Bang theory is reasonably very good in good agreement with cosmic microwave background, and cosmic microwave background can be measured to, let's say, about within 2 or 3 significant digits, very nice. But that's not, we are going to talk about simpler, something much more simple. Or I'm not even going to talk about it, I'm just going to motivate them. So whatever I'm going to do today, I'm just going to use this as a motive. So there is a universe that is expanding. If there is an and I said that it is good because we see in experiments that everything is going away from us. But there is something that is very, very unsatisfactory, and that if there is gravity, let us say gravity is attractive, right? Can gravity be repulsive?
If there's a negative mass.
Yeah, but negative mass has its own issues, like negative mass, we cannot logically. I don't know whether you guys have I given any quiz on negative mass this semester?
Maybe last year.
Okay, if not, if you assume negative masses, it has very illogical conclusions you can make out of it. So, good reasons not to have negative mass. So let's not go into negative. So negative mass is not a solution, and in that sense, it is mostly attractive. Gravity is always attractive, except if you go into energy situation, energy can be negative. Energy is equivalent to a mass. And in that sense, maybe it could be negative, but otherwise gravity is attractive. It's expected to be very attractive. That is, it's very hard to come up with scenarios where it can be negative, unlike electrostatics where repulsion is possible. But now, think of the following
Dark
situation.
energy,
Tell that again.
dark energy. Usually,
Dark energy is what I'm going to motivate, right? So, but that's a word, but here is what you can think of. So let's say there is two masses. Right? This could be any two stars. I think of this as two stars. There is gravitational force attracting them. Think of that as a spring, right? So let's say, sorry, so there's a spring. And now spring is, if I were to compress this, imagine a situation that I compress them and then release them. Right? What do you expect? They will all, this will start moving with velocity v2, this will start moving with velocity v1. Momentum has to be conserved. What did I use this spring for? This is only for the initial push to begin with. Big Bang needs a push, right? So there was an explosion. So spring gives you that explosion. That is the only role of that spring. Otherwise, you can say that it just stays there. It doesn't move. What does move is M1 and M2. So this starts moving, and somewhere very far away, there is this 2 here and there is 1 here. Right? What will happen to the velocity when it is here? So this is the initial velocity. And what can you say about V2 final compared to V2 initial? Remember, there is gravity. M1 is going to be pulling M2. There is no other force we can think of at that scale. When we are talking about the universe scale, electrostatics, everything else comes out to be small because they are all neutral. Every other force does it, at least we know 4 forces. Nothing else is as dominant as gravity when it comes to stars and galaxies. There is no way electrostatics or anything else could. So it is gravity. Gravity 1 is pulling it, so this is going to slow down. So this should be smaller. Right? So initial velocity final should be smaller than initial velocity, or our universe should be decelerating. It is expanding, good. We measured that. That's what Hubble told us. That's very good. But we expect that expansion to be slowing down. Agree? That should be the logical conclusion. But all experiments since 1998, this is very recent. Since 1998, we have been able to measure these velocities very precisely, and it turns out that's accelerating. This has a greater velocity than this. Experimentally, this is what is happening. And we have no answer for that. No one has an answer. The simplest answer is that there is energy in between here, which is negative. And this negative energy behaves like a negative mass, and that gives you a repulsion. That's what is called dark matter, but that's just a hand wave argument. We don't have a very good reason why it is.
just
The-
unknown.
Yeah, the unknown is told, is said to be the dark energy. What we can say is that based on this measurement, that how much should be that matter or dark energy. We can give an estimate on that, and cosmic microwave and all the indirect measurements that we can make, they're all consistent. We can at least tell how much dark energy, and it should be, it is almost 70% of the universe. We are seeing only actually, so 70% is dark energy, rest of the 30% is another problem called dark matter. And that is what we see actually is only about 3% of the universe based on theoretical estimates. So the idea I'm trying to make is that we are missing a lot of like experimental observations do not really match theoretical observations. But inside the solar system, it's perfect. We can predict Mercury's orbit very, very well within probably fifth significant digit. So all that, whenever you are doing theory, the first thing you will question is, was Newton really right? Right? Is it possible that Newton could have made a small error in it? Right? Maybe Newton is mostly right, but you need to put some corrections in them. Einstein made such a correction, but we can always say that, okay, maybe something more than Einstein. So we are going to talk about that, those corrections. Let's say that Newton's law is not really minus alpha over r. Suppose there is a correction done to them. It shouldn't be very big correction because then all our observations will go. So it should be a small correction, which becomes important in some scenario. Right? In most of the scenarios, it's okay, but in some scenarios. So this is a way you can accommodate for corrections. So what we are going to talk about is we will add something here. So we will talk about adding maybe here beta over r cubed, let's say. So this is, we have inputted. Notice this is not there. For now, this is not there. What we did is Kepler problem. This is not there. There are two objects. There is an interaction energy. What are the assumptions we made? That angular momentum should be conserved. dl by dt is equal to 0. That means motion is in a plane. And what was necessary for angular momentum to be conserved? It should be r dependent. It shouldn't depend on the direction significantly. It should be 1 over r. There should be, sorry, there should be no angle dependence. Theta and phi dependence shouldn't be there. So that's why I put beta over r cubed. There is no angle dependence. So angular momentum will be conserved in this scenario also. And energy has to be conserved. So we have your LZ is conserved and the total energy E is conserved, right? Let's say, and next is energy, right? dH by dt is equal to 0. So LZ and E are conserved. So again,
We added beta over r cubed for the angular part.
no, this is not going to be the angle, it's going to be the R itself. Okay. So this is 1 over R, that's a constant. This will again be a constant, depending on M1 and M2, there is nothing else, right? M1 and M2. And but now this will have an R cube, and that's it. So, but R2 minus R1, distance between them.
Why do we add it like that?
That's just a random. So I'm saying, so now, suppose you really care for our planet's not obeying Newton's law, so you really don't like this. And you say that I want to fix it. Now I have all this data, this is not working. And you say that you don't trust any of these calculations. So first thing you will go and say that, okay, let me do my classic calculation with a small change. What's going to be the correction? And historically speaking, in 1880s, this was done in the context of Mercury. Like Mercury goes around the sun, but it precesses, and that's what we will measure. So we're going to make a small correction. It can be any. So the idea is that this could be any form of R, any function that is R dependent, and we will be able to do today's calculation with that. And the question is, can you explain the experimental data? That's the main. So when you are in the unknown, you try everything, because everything is possible at this point. If you make that door open, saying that Newton could be wrong, then immediately you say that, oh, I can use any function f there. And here, I will do a very simple scenario of 1 over r cube, and in the lecture that you have a link for there, I do general f of r also. But here, today, I think we will stick to 1 over r cube. It's mostly the same, nothing changes significant. So that's Kepler problem, and what it involved was, there was a conservation of energy statement. So this is kinetic energy, mu r dot square. This is the kinetic, so if motion is happening in a plane, this is possible whenever r, f of r can be written. Motion is happening in a plane, there is a kinetic energy associated with the radial movement, r dot. That could be an angular movement, that's angular momentum can be written as half Lz square over mu r square. This is the kinetic energy due to the rotation part, plus u of r is equal to E. Right, that was our energy statement, and immediately we made substitution, and the main idea we did was that the phi angular coordinate is equal to r naught dr over, I should define r naught, and this is 1 over e square minus 1 minus r naught over r whole square. Now notice these are your two quantities that are conserved. If you want to describe an orbit, they are decided by how fast you throw something. So suppose I have to send a spacecraft to Jupiter. What do you control? The only control you have is how fast you throw it and at what angle do you throw it, or where you start it from, right? How fast is having vector, so the angle is also involved in it, and from where you throw it from. So let's say if you start it from Florida, it goes somewhere. If you start it from California, it will go somewhere else. Right? So the initial position and initial velocity, those are the two things that decide where it will go and land. Right? That's all, unless you steer it. And usually it is easier to just throw it, like, instead of steering it. So those two quantities are contained in Lz and E. The position is Lz, like you can convert that. So you have R initial, right, and V initial. Remember, Lz is equal to M or R cross P, right? So R cross P. So the moment I have defined my velocity, I have fixed my P. The moment I have fixed my R, I have fixed my position. So I fixed my Lz. And if I pick that Lz to be along the z-axis, motion is happening in a plane. I'm in this plane, and everything else gets fixed. So the only thing that is remaining then is one of the velocity components that is in the radial direction, and that is used to fix my energy. So energy and angular momentum are more sophisticated ways of saying, instead of initial velocity and initial momentum, it's the same idea. And in our equation, they show up in the form of R naught, which is Lz square over mu alpha. If you fix Lz, your R naught gets fixed, and energy is fixed using the eccentricity. Eccentricity is equal to 1 minus energy over effective potential over R naught, evaluated at R naught. So what is the effective potential? Effective potential is this quantity in here. So that's U effective. Now, we are talking about changing the U effective. Initially, this is the Kepler problem. Whenever I say Kepler problem, it is minus alpha over R. Whenever I add it, it's no more Kepler problem. So it was for the Kepler problem we did that. So let's have U effective R, and we will also talk about U effective zeroth order. That means not disturbed. So this is with a disturbance. Usually it's called perturbation. Like these theories are, you know a solution to a problem, you perturb it. you change it a little bit, so this is a perturbation. When I don't put the perturbation, I'll call it zero, that means zeroth order for perturbation, right? So that's my main solution. So here, what we are going to divide is U zero, right? That's going to be my initial condition. So E and R naught are my initial conditions. And the only thing I'm leaving it is that what if there is a modification in the potential when it is moving. In this case, we know that for Kepler problem, for the unperturbed situation, we know that this is a ellipse. And if one of the focal points is your origin, and it turns out that for our purposes, in the substitution that I am going to make, that is my origin, and that's my R, right? That's my R. And that's my R, and that's my angle phi. Okay, so that's the two angles, and there is it's good to know what is R naught, and that's your R naught. I think I didn't stress on it last time. That's that perpendicular line is R naught. And if you have studied mathematical properties of an ellipse, that is what is called a lattice right now, I forget. So R naught or 2 times R naught is I think lattice hopefully of ellipse. That means the length starting from here to there is this quantity of an ellipse. So half of that is exactly what we have. So that's a standard definition for an ellipse. For our purposes, it is angular momentum and energy. And it has this nice feature so that this is our minimum. Right, for the classic ellipse, the Kepler ellipse, our minimum is R naught over 1 plus E. It is minimum because our Kepler orbit has 1 plus, maybe I should write this down. For Kepler orbit, we have R is equal to R naught over 1 plus E cosine phi. So when cosine phi is a maximum, then R is a minimum, right? So it is 1 plus E, and the maximum value the radius can take is R max, and that's equal to R naught over 1 minus E. Okay. And for the Kepler problem alone, this happens at 0 degrees. So this implies that phi is equal to 0. And here, this becomes phi is equal to pi. Only for Kepler problem. If it is not a Kepler problem, what we are going to show is that if this is not the case, this won't reach here. This might be somewhere here. It reaches only there. So there is a small change in the maximum and minimum. And do the same thing while coming back. And that is what is called the perihelion shift, the precession of the perihelion shift. Perihelion is the closest point of our orbit. So when the Earth is closest to the sun, I think that was a question asked last time. That's quiz for you, right? I don't know whether it is June or December. It could be
January 2, I guess.
January. No, it won't be January. It is either December 21st
either December
or June. Yeah, June 21st. One of those. There's 21 plus or minus.
Perihelion is January 3rd.
Not
This one. Sure. I found that one in the room and then I write that one here. Okay, I'll check
Probably
it.
not. Check on. Yeah, probably not. Yeah, shouldn't be. It's one of those equinoxes. That's what unless I'm using something very drastic. Okay, so let's proceed. Okay, so we'll do this. Okay, so now I want to change this expression. And we showed already that of mu R dot square last time was equal to minus U effective. Now I have to, wherever there is an effective, wherever there is an effective potential, I have to say this is zero dot, right, for the Kepler problem. Like there is a minimum value, remember, there is a potential U, this becomes like this, and that was your R dot, and that was your U effective R dot. This is U effective. But now, when I say this, I'm saying this is zeroth order, even though that has been disturbed. This whole potential is disturbed slightly, but I'm still keeping my potential energy to be zero. So the perturbation, you have to ask where all does this perturbation disturb, and we are interested in the dominant part. Okay, so that's our goal. So this one we said is R naught R over R square d phi whole square. Right. And U of R, we said is or can be written if it was minus alpha over R. If it was no, U effective, right? I'm interested in this two together, right? U effective, sorry. So U effective of R is equal to two of them. So I have 1/2 LZ square mu R square and plus, let's first put a minus alpha over R, and then I'll come back and I'll in the same place. So let me write that I'm making a change, right? So this is plus beta over R cube. Right, those are the changes I want to make. This is equal to 1/2 LZ square over mu alpha. Put an alpha there, R naught, then R naught square. Sorry, R naught over R square. But remember, this is R naught. So an R naught alpha over R naught, and then there is a half. This is nothing but minus alpha over R naught times R naught over R. And the next term, I'll write it as beta over R naught cube, R naught over R. I want to write everything in terms of R naught over R. That's the basic idea. And remember again, one of the things that was relevant was we had R naught was this, and one more expression, U effective, zeroth order of R naught was equal to minus 1/2 alpha over R naught. Okay. So this is the same as pull this out. So I have minus U effective zeroth order R naught. So I put in a minus sign. So minus and a minus, that's plus. So this is equal to R naught square over R square. And 2 I have pulled in. So this is minus and a minus is plus. So this is minus 2 times R naught over R. And this is the correction now. Earlier I would have stopped here. In the Kepler problem, I would have stopped here. But this can be written as plus. Right, I pulled in an alpha over R naught, so this is plus beta over R naught cube over, I pulled in an alpha over R naught. So divide that out, but that's also 1/2, so that I'll write it. Let me write that here. So it's 1/2 times R naught over R whole cube. This kind of is interesting. What this means is that this is the correction term. And this is the original interaction energy. At this point, the correction energy will be R naught Q. And if I were to divide this by alpha over R naught, and then just for a factor of half, that's by factor of half. This is a measure of how strong this is. Right? If this is small, this will be a small number. If this is large, then that will be a large number. We are saying that this should be small. In fact, very small. We don't want it to be there in too significant digits, because otherwise all our planetary motion will change. So we want this to be small. So let's call this kappa. This whole thing, we're going to call kappa. That will be 2 times beta over R naught Q over alpha over R naught. That's our perturbation parameter. Every time you do a perturbation, you need a small parameter, which is preferably dimensionless. It should not have dimensions. So that's going to be our kappa. That's our change that we are making. So that's U effective 0 R naught and R naught over R squared minus 2 R naught over R, and so this would have stopped here, plus kappa times R naught over R cube. Why am I doing a cube? Just for fun, like there is no reason why I should do cube. You can try a 4, you can try a 5, anything that works with experiments, or for that matter, any function f of R. If there was a function f of R, this will be f of R naught over R. So we have kinetic energy, we have potential energy. Energy remain the same. We are going to keep the energy and angular momentum exactly the same. Right. There is also going to be a small change in the R minimum and R maximum. That again, we will say we will keep it fixed because these are dependent on LZ. And those dependents, again, in the lecture, I really take care of those changes. But in this lecture, I'll skip that. So I won't talk about the change in the minimum and maximum with respect to the change in the kappa of the interaction. So our equation then becomes this modification where it leads to, notice this 1 minus R naught over R is here. Right? If I add and subtract an R naught, that's where this term is coming in. So what will happen? Where will this penetrate? My new equation becomes E phi is equal to, so this is with perturbation, R over R squared and 1 over E squared minus, so this is 1 minus R naught over R whole square. And there is a new term, and I have to worry about whether it's plus or minus. If this, so I can cheat. Minus. So minus R over R naught over R cube. Yeah. Earlier we had only this much, and this new correction is bringing in a new term. Now, one would expect that this should be straightforward to do, but there is a challenge in this. And remember what we are now doing. First of all, we can try the orbit, but more than the orbit, we are interested in the perihelion shift. And so we would like to do an integral from R minimum, so R minimum to R maximum, which is the same as R naught over 1 plus E R naught over 1 minus. So what I'm not going to be doing is that there is a change in this minimum and maximum itself because of the perturbation. So that we are going to neglect. So again, in the lecture that I give link to, this is my own lecture a couple of years back, because we had more time, we can actually take care of that also and talk about what will be the contribution. Here, keeping time in perspective, so we will just not worry about the change in the limit. And that is how the books usually do. They will not take care of the limits, but it's good to at least consider what might happen if you take care of. Okay. And we are of course interested in so precision of the perihelion. So this is what is called precision of perihelion. That is the closest point. Is it moving with respect to the stars, like with respect to the background? So if you're here and your stars make a design, right? So this is the star structure that you see on December 31st of every year. That will change after 1 year. You come back, your background has changed, right? Exactly at midnight. So if that has changed, but it most of the great accuracy doesn't change, and that precision is equal to 2 times our minimum to our maximum times d5 minus of 2 pi. And of course, if it was a Kepler problem, last time we did that, if you evaluate this for the Kepler problem, this comes out exactly 0. There is no shift, right? But for Mercury, there is a significant means measurable shift. It is not, it's really tiny, but it's a measurable shift. So we have to do this integral. If you do the substitution that we did last time, immediately you will see that there is a divergence. And you will be stuck. I said that there will be a complication that will come up. But what we will do is we will escape that by again using a trick. It's a spurious divergence. Because of the perturbation, you make an approximation and that leads to divergences. But we will see, or in the first step itself, I'll skip that by making a trick. So the trick is the following. It's a very simple trick to avoid the divergence, and I'll show you sort of where that divergence is later on when we reach that integral. So the observation to make is that partial derivative with respect to E, this is a trick. Remember, this is not, E is a eccentricity of the ellipse that's fixed, but it's a mathematical trick. So we can do anything that mathematics allows, right? So this times square root of E squared minus 1 minus R naught over R whole square, and this plus minus kappa over R naught over R cube. What is that equal to? If you were to take that differentiation, that's a square root. You start with 1/2, like power 1/2. Then you subtract 1/2 minus 1, that's minus half. That brings it down in the denominator. Okay, so that brings it down in the denominator. That's E squared minus 1 over R naught over R whole square minus kappa R naught over R cube. But then you have to use chain rule. I only differentiated the square root. E squared is showing up, which is 2 times E. That's a differentiation, but I divide it out by E also, so there's the 1 over E2. So the 2 times E cancels out exactly. So the whole square root can be written as a differentiation. So it's just a mathematical trick, as I said. It is to avoid a divergence, a spurious divergence that will happen. So that will show up. So this is our minimum. Our max d5 then is equal to naught over 1 plus E, naught over 1 minus E, naught over R square. And instead of writing this whole in the denominator, I say it is, that should be perfectly fine. And it is just not for a trick. It is to avoid a big hurdle that we might otherwise experience. Okay, good. This is an integral in R. This is a differentiation in E. I can pull that out. So that's, and you have to tell me, is it okay to do this? What's the mistake I'm making by doing this? That's the only crucial step. So this first step is energy conservation. Energy conservation, if I change my U, leads to this kappa going up. And then I made a trick here, move my derivative out, and I wrote this, and I say, and I cheated.
When it's something subtract.
Yeah,
like
what is
total,
this? Yeah, good.
total derivative you taken.
True, yeah, thinking correct, but can you make it more precise?
So d over d e
Yes.
are not d or whatever square.
This doesn't have any E in it, right?
Yeah.
So I can take this around that. But what I cannot do is that there is an E here, right? So when I moved it out, there is an E that shows up. So I have to hit this, I have to subtract certain particles. Okay?
Evaluated.
So that's what I mean by this is minimum, or this is minimum and that's maximum. So we are asking, how does my perturbation change this minimum and maximum? Right? Earlier it was 0 and pi. And I'm neglecting that here because of time. Okay, but in the lecture we do that. Okay, and again, most of the books do this. They won't take care of this. And whatever we get here, that's usually the answer you will see in at least the standard textbooks. I'm pretty sure they must be explaining this somewhere, or they know what they are doing. It is not a serious mistake. But if you take care of it, that can be done, and that is what is there in your link that is there in your home. Okay, so I'm going to
The
skip.
mistake therefore works itself out.
That's a discussion one should have, right? We can find the corrections due to that. And the question is that the correction that you find because of this, so we are going to get an answer. And it will be a perturbative answer. That means kappa is small. Right? If the corrections due to this is smaller than the corrections that we get, that is okay. Then that's perfectly fine. But what if it is larger? Then our calculation is wrong and the limits are contributing more than the contribution that we have to. Okay. And it seems like this gives you more. Okay, so,
Okay.
but we are dropping, okay? In keeping the time and with the understanding that this is what we're doing, we're just highlighting the point that we can calculate a perihelion shift. But exactly what is our, we don't even know the power of this, right? So this is just an example of how you can calculate the shift in a perihelion, okay? With that idea in mind, now we make a substitution. Right? So we make the substitution 1 minus R naught over R is equal to minus E cosine theta. That's what we did last time also. This time also, we will do the same thing. Substitution, this is R naught. R over R square is equal to E sine theta. Theta. And you have to worry about the limits also, right? So the limit is when R is equal to R naught over 1 plus E, then what happens to theta? Theta is equal to R naught over 1 plus E, 1 plus E, 1 cancels out, there's a minus E cancels out. So this theta is equal to 0. This is the same thing that we did in the last lecture, or the Kepler problem also has exactly the same thing that is happening. So this is 1 minus E, and this gives you theta over pi. That's your limits, that's your integrations, and minimum or maximum E phi is equal to before I make the substitution, I want to do something. Oh, maybe no, it's okay. Substitution, okay. D by dt. This is 0 to pi e sine theta. So this is e sine theta, d theta coefficient, and square root of this is e cosine theta squared. So this again becomes e squared sine square theta, and minus of kappa r naught over r. R naught over r is 1 plus e cosine theta. It's 1 plus e cosine theta. You're doing a cube. That's cube divided by, no, there is no division. That's what we have. We are interested in, this is a hard integral to do, right? But we are doing perturbation. This is small, kappa is small. So I can expand this as a series. So do the expansion in the series. 1 over e by e 0 pi e sine theta comes out, so that is a e square sine square theta, and I'm expanding. Let me write this in 2 steps. So this is 1 minus kappa times 1 plus e cosine theta cube over sine square. E square. Do the expansion. This is equal to 1 over e. E integral 0 pi e square sine square theta. This is your series 1, and I keep only the leading order, so that's minus kappa over 2. That's a power coming in, and 1 plus e cosine theta cube over e square sine square p and plus order kappa square. So that's your correction if you want a small correction. This will be even small, like the second order term. The first term is easy to do, and that's your coupler. Yeah, right. So our minimum, our maximum, 5 is equal to the first term here is e squared. Differentiate e squared, it is 2 times e cancels, it is 2 times integral of sine square theta. That's 0 to pi d theta sine square theta is equal to 1 by 2. Okay, so that differentiation with 2 cancels out, and it exactly gives you the pi, which is the Kepler problem, right? Is half. This is minimum to maximum. So if you multiply that by 2, so that's the 2 pi for the Kepler. And whatever is remaining is what you're having, right? So it's kappa over 2 can come out, and that is 1 over e by e, and there's this e square, and e square cancels. So it is 0 to pi, 0 to pi. and sine square theta all right. This is d theta 1 plus e cosine theta cube. So our del J phi would be equal to the precession due to perihelion is 2 times this minus 2 pi. So when I subtract this out, whatever I get is this quantity here. So it is minus kappa times 1 over e p by dE of 0 pi d theta. Expand this out, 1 plus 3 times, this is a power n. That's a cubic or binomial equation, right? Plus e cube cosine cube. If this integral comes out to be 0, and this integral comes out to be 0. Odd powers comes out to be 0, and this integral gives you that is a 3e squared, and there is a that was factor of 2. I think it's pi over pi. Oh, let's do this. I don't remember if it's pi or pi over 2. Cosine square theta. Cosine square theta is 0 to pi. D theta 1 plus cosine 2 theta over 2. This again doesn't contribute, so it is 1 by 2, so it's pi by 2. So that's pi by 2. Okay. So the integrals are done then. So what we have is this is equal to minus kappa 1 over e partial derivative of e. This integral is pi 0, and this one is plus 3 pi by 2 e squared, and that's it. Derivative of e squared, eventually we have to undo the derivative that we did, so that's minus kappa 1 over e 3 pi by 2 and 2 times e cancels out, and this is exactly kappa 3 pi times kappa. Remember what was kappa? So that's equal to, so this is a dimensionless quantity, right? This is an angle. How much is that angle going to change? So just for reminding ourselves what the factor of kappa was, 2 times theta. Very good. So cube or not cube, evaluate and over alpha over alpha. And in terms of R naught, which is the semi the property of an ellipse, so that's minus 6 pi theta over alpha R squared. So based on those properties, we can exactly calculate that, and does that really match? If it matches with all the perihelion shifts that you can get for all the planets, then you're good. And it should not disturb anything else, like anything else that you've already done, it should not disturb either. So that's the challenge, like it should not make any changes to our current observations, but for some fancy measurement like perihelion shift, it does contribute. That's a calculation for that. Pretty darn close. I think we are close, you know.
No, I don't think so.
You can stop recording and the
Somewhere here. Just, yes.
Again.